In this video, we'll learn more about the organization of the computer. We'll talk about the instruction set architecture, specifically the ISA for RISC-V, and then we'll introduce assembly language, how we write programs for our machine, and look at a couple examples. Okay, so a computer is basically just a device that reads instructions from the memory and then executes them on the hardware. So it's kind of just a dumb machine in that sense, and it just keeps reading one instruction after another in this long list of instructions and executes each one at a time. And there are many different ways to design a computer and many trade-offs involved in how we design these instructions and the hardware that executes them. Specifically, architects have to decide between how to keep the instructions, the number of instructions, simple, so the hardware only has to support a minimum number of instructions, but also powerful enough that it can execute any arbitrary general purpose program. So at a very high level, we can discuss how all modern computers are basically built today, and it looks something like this. We have a CPU, or central processing unit, which is where the instructions are actually executed. And then we have a memory, as we saw last week, and this holds both the data and the instructions. And then we have a bus, or an interconnect, between the memory and the CPU. The CPU will fetch the instructions from the memory and also its data and execute those on the CPU. This is called the von Neumann model, named after a really important person who did a lot of initial research on the computer. This is also sometimes called the stored program model. The final box here that's connected over the bus or the interconnect is I/O, and we'll talk more about this later. This is how we interface with the outside world with input and output. Okay, so remember that we talked about how abstractions are a key part of building systems. It allows us to break down these complex systems into smaller pieces or layers. And one of those important abstraction layers sitting between the software and the hardware was the instruction set, or the instruction set architecture, the ISA. The ISA is a specification for the machine, and it's important because all of the layers above, the software layers above, and also all the hardware layers below, this is the piece that essentially binds them together. And the key word that I like to think of here for the ISA is that it's a contract between the hardware and the software. So this little diagram here is kind of showing stick people as our designers of software and hardware, and the instruction set, hardware designers don't need to know what type of software is, or what type of programming languages or operating system are executed on that machine. They just know that they need to design a hardware such that it meets the specification, the ISA. The same thing is true for the software designers. They just have to meet that specification, and they aren't concerned with all the circuit and low-level details for the hardware. And so we have our stick man down here at the bottom and the hardware designer meeting the specification for the instruction set, while the software designers on the top are running around and playing, creating all the fun things that's designed based on this instruction set. So what goes into the instruction set? Well, one key piece you can probably guess are what are the operations, or what are the actual instructions that the machine supports. Another important piece are the instruction formats, and we'll talk more about this as well when we implement our machine. How are the instructions represented in terms of which bits or which fields contain which pieces of data? ISAs also describe how we address memory and access data with the instructions, as well as any exceptions or exceptional conditions. All of this goes in to the ISA specification. Okay, so now let's talk a little bit about the ISA that we're going to design for, specifically the RISC-V instruction set, to build our particular machine, the Otter. An important piece of the ISA is where do we keep our data, and specifically how many registers, what type of registers do we have. So in the case of the Otter and the base RISC-V specification, RV32i, we have 32 registers, shown here on the right, listed from X0 to X31. And these are all 32-bit registers. In general, we're going to be building a 32-bit processor. The width of our data path is going to be 32 bits. These registers also have some other names. We'll talk more about these later as well that we can reference in our assembly programs. But let me also point out one key register, which is X0, in that it actually doesn't hold any data and is instead hardwired to the value 0. We'll see later how this is useful for optimizing our programs and writing certain instructions. Another important register is the program counter. This is also 32 bits. This is really important for von Neumann architectures, as this is the register that's going to tell us, or tell our machine specifically, which instructions we're currently at in the program, keeping track of what we're executing. We also have the memory with different segments for different pieces. We've already seen how the memory is going to hold our program. We also call this the text segment, as well as data, and we'll get into more of these other segments later. There are roughly 30 instructions that we're going to support in our system, the base instructions. We have obviously some instructions for doing arithmetic, adding and subtracting. We'll have logical instructions. We have some instructions for comparing. We'll talk about instructions for transferring data to and from the memory, and then also instructions that modify the control flow for the program. So I also want to quickly point out on Polylearn, under our auto resources section, you can actually go ahead and look up the formal RISC-V specification. So RISC-V is a new ISA design, and it has a lot of really nice features. It's built to be very modular. It is entirely open source, so if you decided to create a product, you could do so, make your source code private and not have to pay any royalties. The instruction set which we're designing our machine, our Otter for, is called RV32I. It's a 32 base integer instruction set. And this is a relatively short chapter, about 15 pages, and I would recommend have a look at it. It's very concise, unlike other ISAs that have manuals that are hundreds of pages long. Okay, but back on Polylearn, we also there's a reference sheet. We also have our Otter cheat sheets, which we'll refer to frequently. And these have, on the first page, all the base instructions that we're going to be implementing, as well as some pseudo instructions, which I'll talk about in a second, as well as other information, including the instruction formats. So we'll be referring to these a lot in the coming weeks. I've also uploaded here chapters from some related textbook, which everyone should read, as well as a link to a simulator that has support for most of the basic assembly instructions and directives, and is a tool that you can use, that you can start getting used to assembly programming. Okay, so back to the slides. Okay, a little bit about the software flow then. So machine code is what actually is going to be fetched from the memory, where we store our program in memory, and the computer is going to read these binary values representing our instructions and execute them on the computer. We're not going to want to write long programs with machine code, so instead we're going to use assembly language, write our assembly code, and then use an assembler. In the case of the simulator I just showed, it also has a basic assembler, and we also have some other tools that we'll use later to take assembly code and translate that into machine code. And we can also use the same tool flow to take high-level code like C code, and we'll do this later in the quarter as well, and compile this down into machine code as well. So let's talk a little bit about assembly language now. So assembly language is basically just a convenient way that we could represent the machine code. And so they're just strings or some symbols that will get translated down into the machine codes, the ones and zeros. The nice thing about assembly language then is that it's going to give us a good understanding of the underlying hardware. It can allow you to write more efficient code or get speed ups. In fact, in the past 10 to 15 years, the compiler technology has improved significantly, reducing the time that most programmers spend actually writing assembly code. But it's still very useful to learn assembly programming because it gives you a better understanding of how high-level code is actually executed and can lead you to writing better and more efficient high-level code. In the end, I think you'll find assembly programming kind of fun. It's sort of a game figuring out how to most efficiently write code to solve some kind of simple and also very important problems. But in the end, I just wanted to point out that assembly programming is essentially all about just pushing a bunch of bits around. So this is an example of what an assembly language program looks like. There are a couple key parts of the program here. First of all, anything with a period in front of it, these are called assembler directives. If you've done C programming before, these are sort of like preprocessor directives. These are not translated to assembly instructions. Instead, these are commands or options that we're communicating to the assembler. The actual assembly instructions are listed here. And so for the first symbol or the string here is the name of the instruction. And then we have the parameters or the operands to that instruction shown here. Anything with a pound sign, these are comments ignored by the assembler. We also have labels at the beginning of the line here, followed by a colon. We'll talk more about this in the coming lectures. Okay, so as I said, the instructions usually have some operands, although they might not have any, depending on the instruction. Most of the instructions for the RV32I, the RISC-V ISA that we're meeting, are going to have 3 operands. And these operands can come from different places. So some of the operands can come from registers, and that's shown here. So we have an AND instruction, and we have 2 input registers, X5 and X4, and the result or the destination of that AND is going to go into the register X6. We can also have operands that come from the instruction directly. They're encoded directly in the instruction. If it's a small enough value, we can do this, and these are called immediates. And so in this case, we have an immediate value, 11F. Remember, 0x signifies we have a hex value. And so this instruction has both register operands as well as a immediate operand. We can also have operands that come from the memory, and we'll talk some more about this as well because these are an important set of instructions too. We'll use a register and an immediate value to specify an address in the memory where we'll retrieve the data, in this case to put it into another register X5. Important piece here to realize though is that operands can come from different places, and they also have different associated performance impacts. Immediates, in terms of performance, will be the best because we don't have to take up a register to store our data. We can encode it directly in the instruction. Registers would be our next choice, but we're limited in the number of registers we have, so memory will be where we'll keep most of the working data for our program, and we'll bring this into the memory using these special instructions, loads, and stores. Okay, so the first instructions we'll talk about are the data processing instructions. These are the actual instructions that do the number crunching, the actual calculations, and we have a set of arithmetic and logic operations. So we have add, subtract, and then we also have logical operations to do exclusive OR, XOR, OR, and. Each of these takes two input operands, and they can come from two registers or a register and an immediate. However, with subtract, notice that there is no subtract immediate instruction, but that's okay because what we can do is we can use the 2's complement of the second number. So for example, if I wanted to subtract 1 from a register, say X5, put the result in X5, I could write my assembly code like this. I could also, let's say that I wanted to subtract the contents of X6 from register X5. I can find the 2's complement of X6, remember this from 133, and I can do that by inverting all the bits and then add 1, or I can also do this another way. Subtract X6 from X0, remember X0 is hardwired to 0 to get negative X6, and then add X5 and X6. In fact, I believe we have a pseudo instruction for taking 2's complement or negating the value as well. So let's talk about pseudo instructions for a second. So as I said, on our cheat sheet on that first page, we have about 30 or 31 base instructions. These are the actual instructions which our machine, the Otter, will execute. To make our life a little bit easier, we also have a set of pseudo instructions, and this is on the second page of our cheat sheets. And these, while not being actual instructions, the assembler will take care of translating these into base instructions for the machine. So an example of a pseudo instruction is move, shown here. So if I wanted to move the contents of one register into another, I could do something like this and write in my assembly program, move RS, the source register, into the destination register. The assembler will see this and translate this into base instructions, in this case just one base instruction. In this case, it would just be an add immediate instruction. Another useful pseudo instruction is the load immediate pseudo instruction, or LI, and this puts an immediate value into a destination register. Now this may also translate into an add-I instruction like this, but it may also translate into a different sequence of instructions, or the assembler might find other clever ways to implement this if it's already in the code, depending on this immediate and the register value. So if this is a larger immediate value, then it's, for example, going to need to do something different. And so we'll see this more when we start talking about the instruction formats. But from the perspective of the programmer, you writing code, you can use this to put immediate values into a register. So the ISA also has a way of generating these large immediate values, and there's two ways to do this. So one is with something called load upper immediate, LUI, and also add upper immediate to the PC. And these are base instructions. So the LUI instruction puts into the destination register the immediate value, which is encoded in 20 bits, and puts 12 zeros at the end. The AUI PC, or add upper immediate to the PC, generates an immediate value that's relative to the PC, meaning that it adds to the program counter, the PC register, the immediate value with 12 zeros at the end. So depending on the program and what we want to do, we can use these two base instructions to generate larger immediate values.